Our goal for this project is to predict quality of white wine based on its chemical properties. To do this, we use PCA to reduce the dimensionality of the data and uncover patterns that aren't obvious for individual features. Then we applied a decision tree model to make interpretable predictions about wine quality based on those chemical characteristics. The broader purpose behind this work is to provide valuable insights for winemakers and quality control teams in the wine industry. By understanding how different compounds impact perceived quality, producers can optimize their processes and consistently deliver higher quality wines to meet consumer expectations.
So we used the white wine quality data set, which is available on Kaggle and originally published by the UCI Machine Learning Repository. The data is based on Vinho Verde wine samples from Portugal, and it includes numerical features such as acidity, sugar, alcohol, and other physiochemical properties. As a first step, we performed data cleaning and exploratory data analysis to better understand the feature distributions, detect any outliers, and prepare the data for modeling. So let me share what that Jupyter Notebook looks like. So first we had imported the data, see what it looks like, and then identified any duplicates in each column, and then dropped it. And then seeing if there's any outliers using standard deviation, identifying them, and then plotting them in box plots to really see where they are located in each of the variables, and then also seeing the distribution for each variable. And lastly, we created a correlation heat map to see which variables are really highly correlated as part of our EDA. So let me go back to the slides. So what are some of our key findings that we uncovered? There's 3 key findings from our analysis that could really help winemakers improve their wine quality. First is the alcohol content is the strongest and most consistent indicator of high quality wine. Both the principal component analysis PCA and the decision tree model point alcohol levels above 11.7 as being the hallmark of having higher quality wines. This insight suggests that winemakers should focus on optimizing the fermentation process practices to increase alcohol content while keeping the wine balance. This approach could lead to better wine scores overall. We also find that volatile acidity, sulfur acid, and chlorides are critical to monitor in order to prevent quality drops. PCA show a strong negative correlation between these compounds and wine quality, often due to spoilage or off flavors. The decision tree reinforces this by using sulfur dioxide as a key decision point, especially in wines with lower alcohol content. Winemakers should closely monitor these factors during production as they may serve as early warning indicators of potential quality issues. And third is consumer preferences to create opportunities for winemakers to target niche markets. PCA components like PC 5, 6, and 7 reveal that certain components typically are considered negative, such as residual sugar and chlorides. And they both can actually enhance wine quality in specific contexts. This opens the door for market segmentation, where winemakers could create tailored wine profiles to suit consumer tastes, such as sweeter or more mineral-forward wines. In summary, these findings suggest that winemakers should optimize production process based on chemical properties, creating unique wine offerings that improve overall quality control, leading to better market alignment and consumer satisfaction. So let me talk a little about the decision tree model. We decided to use the decision tree because it was easily interpretable. This allows us to provide actionable insights for winemakers who may be asking questions. For example, we can make suggestions such as keeping the volatile alcohol content above 11.7% for higher quality wine. And by visually tracing the path from the root to the leaf, winemakers could see exactly how the model predicts low, medium, high quality wine for any samples. So here is the Jupyter Notebook that showcases this. First, we load the data sets, double checking that the data doesn't have any null values. And then to simplify the problem, since human testers score wines from a scale of 0 to 10, we group these scores into 3 buckets: low quality, medium quality, and high quality. As you can see here, most of the wines are classified as medium. And to evaluate our model, we held out 30% of the wine as a test set and the remaining as a training set, which the model actually learns from. And then as you can see here, we kept the levels at 3 because it's the level that we could see most of the notes and also interpret them. For example, here you can see that if the alcohol content is greater than or less than 11.7, it often leads to lower quality classes and medium, indicated by the green for low and a purple for medium. And then if it's above, it leads to higher quality wine showcased in orange. And lastly, we evaluated the model using accuracy, precision, and recall. And with the accuracy of approximately 71%, it means that it's correctly classifying 7 out of the 10 wines.
And next, we did PCA. We weren't sure if all 11 chemical features were equally important or if some were redundant. By running PCA, we were able to identify combinations of features that drive variation in wine quality. To determine how many components to focus on, we examined the explained variance. By selecting 8 principal components, we captured about 90% of the data's variation, allowing us to simplify the model without losing essential information. We then examined each component and visualized the relationships between quality and the key contributing factors. This allowed us to better understand how different variables, both individually and in combination, impact wine quality. In components like P1C and PC3, we saw strong negative loadings on compounds such as volatile acidity, chlorides, and sulfur dioxide. These are often associated with spoilage or off flavors, which makes them red flags for quality control. On the other hand, higher alcohol and lower density or sugar consistently aligned with higher quality wines. But quality isn't just chemical, it's also based on consumer preferences. In PC5, 6, and 7, we found a surprising twist. Variables like residual sugar and even chlorides, which were negative in earlier components, showed positive associations with quality in some contexts. We also found that acidity, citric acid, and pH, highlighted in components like PC2 and 8, interact with quality in complex ways. This challenges the oversimplified idea that more acidity equals better taste. So here are some key actions for winemaking. Winemakers can optimize fermentation practices to maximize alcohol content while minimizing sugar density and sulfur dioxide for higher quality wines. They should also monitor volatile acidity and chlorides as key indicators for spoilage or off flavors to prevent low quality batches. Additionally, winemakers can create tailored wine products for niche markets by adjusting residual sugar and chlorides to suit consumer preferences or sweeter or more mineral-forward wines. They can also adjust production volume, pricing, and marketing strategies based on predictive insights to better align with market potential and consumer demand. And that sums up our presentation. Thanks.